Hello Algebra 2 students, and welcome to Chapter 6, Exponential and Logarithmic Functions. In this section, we're actually going to be doing just 6 of these sections, 6.1 to 6.6. And today you can see we're going to be starting with exponential growth and decay functions. But as we go through Chapter 6, we'll be looking at different things, specifically called the logarithmic functions or logarithms. So you can see 6.3, 6.4 has that. And 6.5 has that, 6.6 has it as well. We're looking at, eventually looking at solving equations with exponential and logarithmic functions. So we're going to be getting into some graphing again today. We'll be looking at some transformations also with the graphs eventually in 6.4. So here we go, 6.1. We're looking at exponential growth and decay functions. So what we're going to learn today is we're going to graph some exponential growth and decay functions. We're going to use exponential models to solve some real-life problems as well. All right, so let's take a look at a quick little cartoon from Calvin and Hobbes. So we got Calvin in the little cart there. It says, "There's a new girl in our class." "Well, what's her name?" Hobbes says. "Who knows?" "Is she nice?" "Who cares? Not me." "Do you like her?" "No." So Calvin and Hobbes. Remember, Hobbes is his little stuffed animal, but he pretends that he's real, a real tiger. Okay, so on page 156 there in your notes, the top you'll see your vocabulary. So here's some vocabulary to put down, starting with exponential function. Really, when that one you want to just kind of put down, or I'll highlight what you need to write here. So what you could write here would be just an exponential function. It has the form of this right here. So basically y equals ab to the x power. So an exponential function, and you can write this in here, is when x is in the exponent spot. And that's what you want to put down really in words, is just that x is in the exponent position or exponent spot of the equation or of the function. Y equals ab, and then x is the exponent. That's an exponential function. It says where a cannot equal 0, because if a equaled 0, this whole thing would be 0. And the base b is a positive real number, okay, other than 1. So this right here, base b, is some positive number other than 1. And here we have it says if a is greater than 0 and b is greater than 1, then this is an exponential growth function. So that's what you can put down for exponential growth function, is basically right there. If a is greater than 0 and b is greater than 1, it's going to be exponential growth. So, basically this has got to be greater than 0, so it can't be negative. So that's not a negative number. And the b has to be greater than 1, bigger than 1. If it's more than 1, it's going to grow. And that's what we're going to really see with this base number here. If it's more than 1, it's going to grow. That b is called the growth factor. So you can say growth factor really is the b in the function. That is the growth factor. The simplest type of the exponential growth function is just this, just b to the x. So like basically a would be 1. Okay, so if a was 1 here, a is a positive number. If it's 1, then it would just be b to the x power. That's the simplest, like basically parent function you might want to think of the exponential growth function. And so what we see here, this is what that is. So the parent function for the exponential growth is just this right here. You can actually write this down next to here. Actually, it's in here. There it is. F of x is f of x equals b to the x right there. So you can see it right there. And it says where b is greater than 1, that means it's growth because b is greater than 1. It's the parent function. It looks like a Superman ride graph if you look at the shape of it. So if you remember the Superman ride from Magic Mountain, that's kind of what these exponential functions are going to look like. Superman ride graph. This one's going to be going up from left to right. So it starts over here on the left and it's going to start to zoom up. That's a growth function. We're going to see the decay ones here in just a minute. The word asymptote, you want to highlight that right there, or this whole part right here. This is what the asymptote is. I know that's in your vocabulary. You don't need to write it down in the vocabulary. You can just highlight it right here. So basically an asymptote is a line that the graph will get closer and closer to but never touch. And so that's what it says here. It approaches more and more closely. but it's just never going to touch it here. So it looks like it's right here starting on the x-axis. It actually never really touches the x-axis. It just gets closer and closer as it goes out this direction, and it will never actually touch it. So basically I always think of this line right here, that asymptote, is like the platform for the Superman ride, because obviously if as it comes down you wouldn't want it to actually connect with the platform. That would kill all the passengers. So it just needs to be right on top of the platform. It gets closer and closer to that platform until it comes to that stop eventually, and so where people can get on and off, but it actually never really connects and collides into that place. So it's an asymptote that it cannot touch. And so if you just remember that the asymptote is that line, it's like a line that just cannot touch. It's kind of like maybe a force field as well, or something like that. You might want to think of it as that. You just cannot touch it. Alright, so let's look at our decay functions. That's the next one here. So the decay functions, we have exponential decay function. Basically it's like the same thing right there, a, b to the x, but this one's a little bit different. For the decay, you want to say this: well, our a is greater than 0, but the b, and here's where the difference is b is between 0 and 1. So the growth functions, a was also greater than 0, but the growth functions, b was greater than 1. And this one, b is in between 0 and 1. So that's what a decay function is. So you may want to just put that down there. It's between 0 and 1. So it's some fraction, it's some decimal number that's less than 1, but obviously it's positive, so it's definitely going to be positive. And the decay factor, that's also b as well. So b is either the growth factor or the decay factor, just depending on whether you have exponential growth or exponential decay. The parent function for that one here, again, you'll be still saying the same thing. Here's our b to the x power, but this time b is in between 0 and 1. And you notice the difference on this one, from left to right, it's coming down. It's like landing, basically. So it's just coming down. It's like you're looking at the Superman ride from a different perspective, from the different side, and it's coming down from left to right. And so that's where it's coming up, from way up here to infinity, and it just keeps coming down. It gets closer and closer to our asymptote again, which in this case is the x-axis again. So sometimes the asymptote line here will move, because this could move up and move down. We'll see that when we talk about transformations though. But right now we're just going to see this asymptote line pretty much be the x-axis for all of these. Alright, so obviously we can see the domain on this one is all real numbers. The domain, it's going to be left and right. So for the growth or decay function, it's going to be all real numbers. That's one thing you want to realize. Where's the graph on the x-axis? It is all real numbers. The range, however, is going to be an inequality, because obviously the graph is not below the x-axis. It's not even touching the x-axis, so we're going to say it's just greater than 0. It's not equal to 0, because that means it would touch the x-axis. So it's just above here. Above the x-axis means it's greater than 0. So that's what our range on this one's going to be. We can't put the little equal to sign there, and if we did, that means we would be killing all the people in that ride. Okay, if you turn over to page 158, our first 4 problems in the extra practice. So what you want to do on these ones is we're going to graph these eventually, so you can draw your coordinate planes on here. They're pretty much the same for every single one, almost. See, most of it's going down straight through the middle, and then putting your x-axis there at the very bottom, just one box up for each of these. Looks like this one's going down through the middle. On this one though, you can see I'm going 3 boxes over, so this one's not quite in the middle. So I would do that one, and this is the last one, number 4. Go 3 boxes from the left, and then do your y-axis. So up here it says, tell whether the function represents exponential growth or exponential decay. So first of all, we need to realize, again, what is the difference between exponential growth and exponential decay. So what we have here is we have our b numbers. These are all our b numbers here that's in the parenthesis. It's what's being affected by the x. In fact, the a number would be in front of this. On all of these, the a number would be 1. This is our b number here. And maybe I'll go back at the end and kind of highlight that. But right now we need to see our a number is 1, because we don't see the a numbers. The a number is 1 for every single one of these. In the parenthesis is going to be your b number. That's the base number to the exponent of x. And remember, when it's growth, that b number is greater than 1. If it's decay, that b number is between 0 and 1. So number 1, we can look at this b number here, 1/12. That is definitely not greater than 1. That is a fraction between 0 and 1. So right away, let's go through all 4 of these first and just decide if it's exponential growth or decay. Our first one is decay because of the fraction here of 1/12. This is less than 1, obviously greater than 0. It's not negative. It is positive, but it's less than 1. Number 2, 1.5. Well, obviously that's more than 1. 1.5, that's like $1.50, which is more than $1. So this would have to be growth here in this case because it's more than 1. If we look at number 3, 7/2, an improper fraction is always more than 1. This is a proper fraction, less than 1, but 7/2, your numerator is bigger. So this is going to be actually, be more than 1. So that's growth, because it is more than 1. This one is 0.8, 0.8, so that's less than 1. It's like 80 cents if we want to think of it in terms of money, which is less than $1. And so that's going to be decay because it's less than 1. So 1 really is, the number 1 is really the cutoff between growth or decay. If it's more than 1, it's growth. If it's less than 1, it's decay. Obviously the b has to be positive. So you wouldn't be ever seeing a negative b number here. So you just need to know, remember 1 is like the division between growth and decay. If it's more than 1, it's growth, less than 1 is decay. Alright, let's get into graphing these now. So we know this one's going to be decay, which means it's going to be coming down from the left to right. So we're going kind of coming down to this. Our x-axis is the asymptote. It's going to get closer to that but not touch it. And we know that just because it's kind of more of the basic one. It's just b to the x. And that's always going to be your x-axis as the asymptote. As we start to see things change, we'll see some transformations happening a little while later and see how they look a little different. But we're just getting used to just the basic kind of parent functions for these, which is just the b to the x. So these all would be kind of considered parent functions in this case because they're just b to the x. So we're going to start off with just the little table of values, and that table of values that we're going to put here is just 4 numbers, and we're going to be right around 0, and we're going to just start with -1, 0, 1, and 2, and those are the same 4 numbers we're going to use for every single one of these. Now these are the best numbers to use it when you just have a b to the x. If you got something bigger or something more going on where it's going to be some kind of transformation, then we might choose different ones. But right now, if it's just b to the x, these are the best numbers to use, right around your origin here. So when you say -1 for x, that means your exponent now is going to be these numbers. These are all the exponent numbers that are going to be plugged in for x up here. If I plug in a negative exponent, what's that going to do is, for a fraction, that's going to flip the fraction upside down. And so that's what we're going to see here. So for -1, it's going to flip this around and make it 12/1, which is just 12. And so we can plot that point. I'm going to go every box worth a half. So I'm going to go -1 is just halfway here, and then 2, 4, 6, 8, 10, 12. And there's -1, 12. So this is going to be every box is worth 2 here. So 1 is just halfway. -1's halfway there. So 0, if I plug 0 in, 0 should be the easiest one because anything to the 0 exponent will always equal 1. So that will always be 1 for all of them. When we plug in 0 here, it's going to just make this into 1. We need to remember that when this is a 0 exponent, it always gives you a 1 as an output. So we can plot that also just right there on the x-axis, or sorry, on the y-axis. So right there, just go up 1, it's only going to go up a half then of the box. If I plug in 1, it's going to give me exactly what I have, which is the 1/12. So I'm going to get 1 and then 1/12, which is, 1 is going to be here, 1/12 is just going to be barely up, just really close to the x-axis there. So I'm just going to put it right on top of the x-axis. And if I put in 2, if I put 2 here, that's going to basically, 1 squared and 12 squared. So we know 1 squared is 1, 12 squared is 144. That just makes it even closer to the x-axis here, where you can barely even see the difference. It's going to be even closer there. So I put it there, but we're going to see it just kind of coming down. It's going to get closer and closer to this x-axis. So as we graph this now, it'll look like that. Just combining your points, connecting your dots, you're coming down, and then you're just going to start to come out and kind of land that, car from the ride we were talking about with Superman. All right, this next one with growth, this one's going to be coming from the left to right. It's going to be going up like this with growth. Same table of values. We're going to plug in -1 up here. Sometimes it might be easier to see the decimal as a fraction, so let's realize that that decimal is really the fraction of 3/2. So that's something you might want to realize, that it is 3/2. You can kind of think, well, 0.5 is a half. This is like 1 1/2, which is 3/2 as an improper fraction, because you want to make sure you see that, so that when we plug in -1, we can just flip this upside down. And so it's going to give us 2/3. Okay, so as you can see, we're going to be going by ones here on this graph. So as we plotted this -1 2/3 point, we're right here. So -1, we go up about 2/3 of the way. And then if we plug 0 into this, it's going to be the same result as we had over here. It's going to be 1. Anytime you have a 0 as an exponent, it's going to be 1. So then we're going to see our graph going right there. So 0, 1. I have a point right here next. And then we put -1 in for x here. That's just going to give us the same thing we have, which is a 1.5. So we're going to get 1.5 for that one. So if we come over here to 1, we'll go up 1 1/2, so about right up in that area. And then we plug in 2, so now it'll be 1.5 to the second power. Basically 1.5 times 1.5 is what we'll get there. That's going to be 2.25. You need to do that on the calculator. So when we come over to 2, we're going to go up to 2, and then about 1/4 of the way up, a little bit more right there. And you can kind of see the ways this is kind of going, so we can now kind of just draw our curve that would follow that. Now notice I did put one more on this one. This is why I did that. I added 4 in here just to show that, that we can maybe get a little bit better of a idea of how the curve's going if I know where this one is, or where the 4 is over here at the end. So if I do plug in 4, that's 1.5 times itself 4 times. So if I did that, just kept on doing 1.5 squared, there's that 2.25, and then I'd say, okay, now times 1.5 again, that equals that number, and then times 1.5 again, this will be to the 4th power now, that's 5.06, so that's about around 5, we can say. So it's about 4 from all the way over here, and then 1, 2, 3, 4, 5, right about in that area. And so that's where we can put our next point, and then we'll just draw our curve from that point. So remember, it's going to come down this way. As it goes off to the left, it's going to get closer to the x-axis, but we won't cross the x-axis. That would kill all your people in the car. So remember, you got to keep going up this way, come down. Your asymptote is the x-axis. Okay, for this one, let's do the same thing with the same numbers. Starting with -1, now we're going to flip this upside down, and we may also want to see that as 3.5. So we might need to use the 3.5 at some point. So you just need to realize what the fraction is also as a decimal, and the decimal sometimes as a fraction. So, but on this one, I can just flip this upside down. That would give me a 2/7 then for the -1. When I have -1 as an exponent, flip the fraction. And so that one will be down over here. We're going to also go by, every box will be worth 2 again. So I go -1 is halfway. 2/7 is not very far up. And we know we're going growth here on this one, so it's going to be like the last one. It's going to be going up here from left to right. Plug in 0, we'll get the same result. We're going to get 1. So if I go to 0, 1 is going to be just halfway up on the box. So there's 1. And if I plug in 1, I'll get the 7/2, which we might want to then use that 3.5. That might be easier. So I go here to 1. There's 2. 3 would be halfway. It's going to be up a little bit higher than that, so you can see where that is. And then if I plug in 2, plug 2 in, we can say we can square the top number, square the bottom number. That's going to be 49/4 as a decimal. That's 12.25. So that might be easier to figure out. So if I come over here to 2, which is be here, so we can go 2, 4, 6, 8, 10, 12. So it's going to be a little bit higher than that point. We'll put our point up there. And now we just follow that curve going up. And remember, our x-axis is the asymptote. So as I come down this way, I'm not going to cross the x-axis. So it'll be looking like something like that. On 4, it says decay, so we're going to be more like number 1, where it's going to be coming down from left to right. And I'm going to use the same numbers. So if you start off with putting -1, it might be helpful to make that into a fraction. So 0.8 as a fraction will be 4/5. And so if I flip 4/5, then that's 5/4. So 5/4 is the fraction, which is also a 1.25 decimal. So that might be helpful to see it as a fraction, flip it, and then you can make it back into a decimal. Where our point's going to be, we're going to go by ones on this one. So we will go by ones. Every box is worth 1. Come over to -1, and there's going to be 1.25 up. And then for 0, we'll get 1 again. And where that will be just right here on the y-axis. Plug in 1, we're going to get 0.8. And so that's just going to be coming down a little bit further. So 1 will be at 0.8, a little less than 1. Plug in 2, we're going to get 0.64. So we plug in 2, it's going to be over here. So 0.64 is again a little bit higher than halfway. And we get the idea that this is not straight. This is going to be kind of a curve coming down here. So we kind of make this into a curve coming down. It's not going to cross the x-axis. If it was straight, it would probably cross right about there. But we're going to make this a curve and come down, and the x-axis is the asymptote, and it's going to be kind of going up that way. So something like that. Just kind of get it's a little bit wider of a curve. It's not so pronounced like some of these were. Okay, so here's some notes I'm going to have you copy down on page 155, the top half of the page, underneath the exploration number 2. Right there is a nice big wide space for you to put this in. And what I need to copy, what I want you to copy down is what I boxed here. These two exponential growth model, exponential decay model. So copy those two down. And then you're also going to copy down what the A, the R, and the T stand for. So put that right there on 155, the top half of the page. So they're very similar, as you can see. The one difference between the exponential growth and the exponential decay model is the sign that's in between the 1 and the R here. So they both have an A, R, and T, but this is a 1 plus R for the growth model, 1 minus R for the decay model. And the reason for that is because growth is always going to be more than 1. So no matter what you put in here for R, what number you put in here for R, which is the rate number, as you can see here, it would be a percent of increase or decrease, which is a rate, it's a percent. And whatever we put in here as a percent, we would make that into a decimal. That's always going to be more than 1 when we say 1 plus some decimal. But here we're going to say 1 minus some decimal, so that's going to actually become less than 1. That's why it's decay. And so A is the initial or starting amount. So when you look at this A number here, that's what it would refer to, is the initial or starting amount, because we got to realize that most of the time we're going to do these is in real life quantities. We're going to see real life problems here, and we're going to use these models for growth and decay. So A is an initial amount or starting amount that you have. Sometimes it might be money, sometimes it might be a certain population you're starting with. Rate's the percent of increase or decrease. It's in decimal form when you plug it into the formula. Okay, so obviously, if it's more than 1, it's going to be increasing. If it's less than 1, it's going to be decreasing. And then the T just stands for time, how much time goes by. And usually that's in years. A lot of times it's years. But other times it might be in days or months or something like that. Okay, so I'm going to have you put this problem here at the bottom of 156. So this is a population problem. So in 2000, and you can kind of copy down this information here, just the problem, you want to write that down. In 2000, the world population was 6.09 billion. And during the next 13 years, the world population increased by 1.18% each year. This is a very real problem to us today. We're in 2019 at this point, and it's going to be, even different than it would be, and we can figure that out. Or whichever year we're in, we can figure out what that is if we even just use that percentage rate. Now this sometimes fluctuates here, but this is, again, they're saying it's about that for each year. So in 2000, it was almost a little over 6 billion people. So it says write an exponential growth model, because it's growing, population is growing after T years. So which is after 2000. So write an exponential growth model given the population y in t years after 2000. Estimate the world population in 2005. And then estimate the year when the world population was 7 billion, or estimate the year when the world population was 7 billion, or when it will be. Let's just do A though right now and figure out that one. So first of all, we need to realize that the A number here, the initial amount, the starting amount, is the 6.09. The rate here, we're going to change this percent into a decimal, so our rate would be this 0.0118. And we're just going to plug that into the growth model that we were just talking about. It's right there. So there's our growth model. A is the 6.09, 1 plus the rates, 1 plus that decimal, and there's the t of time. And that's it for as far as writing the exponential growth model. That's the growth model right there. Then it says to look at it in terms of, when will it be, or estimate the world population in 2005, which is 5 years later, so t would be 5. So you plug in 5 for that, and then we would just use a calculator to figure that out. So if we did that in the calculator here, we would want to first figure out what this to the 5th power is. So it would be a 1.0118, and we're going to raise that up to the 5th power, so I'm going to use that button. It's going to put a little caret on my screen, and then 5 is the power, and that will equal this number. Then we're going to multiply that by 6.09, so times, which is here, this little asterisk is times 6.09, and equals, that gives us a 6.457. They're going to round it off to 6.46 in billions for this one. So what you could do right now, and I'll just give you a minute for that, I'm not going to show this to you, but you can figure out, estimate the year when the world population was or will be 7 billion. When will that be? So to figure that out, you would have to say that the y is actually 7. And then you could figure that out by trying to solve for t, which is going to be a little more challenging to do. So that's going to require more of a logarithm function to be able to figure out and solve for t in this case. So that's why we're not going to do that. I'm not going to show you that one, but we will get to that one when we get to logarithms. Yeah, here's another one from the book. You don't need to copy this one down. This one's going to be like our number 5 on the extra practice. But basically it says the car value can be approximated by the model here, where t is the number of years since the car was new. So first of all, A says tell whether the model represents growth or decay. And then identify the annual percentage increase or decrease of the value of the car, and then estimate the value of the car, or estimate when the value of the car will be $8,000. So time on that one, we're looking for time. And so in this case we'll look at first of all A. So the base of this is 0.85. So we want to think about that our model would be at it's less than 1. Okay, so since this is less than 1, we know it's decay. So it has to represent decay because it's less than 1. It's greater than 0 but less than 1. Identify the annual percent increase. So here's where we got to go back to that model we were just looking at, the 1 minus r inside the parenthesis. So basically 1 minus what number would give us this 8.5, and that's, you can set up an equation like that. You can say 1 minus r equals 0.85, and then solve for r. So that's something you could do to solve this, but you need to figure out that the r has to be 0.15. 1 minus 0.15 gives us this 0.85. So that if I make this my r, now my rate here is going to be 15%, and it will be a decrease because it's decay. So if you have decay, it'll always be a decrease. If it's growth, it'll always be increase. And then estimate when this will be. So now we are looking for time. So basically your y is 8,000. So here's kind of how you would do this without using logarithms, because we can use logarithms, and we'll look at that later. But what we could do is we could graph this. We could look at the graph and decide where it is on the graph. So if I say, okay, 8,000 is here, so basically my y is 8,000, what is my t? Or my t is like my x in the problem. So I can look at a graph and see, okay, when y is this 8,000, so we're going up here by thousands, so kind of looking at this in terms of the thousands, where would it be? So x equals 7 when y is about 8.00, so this is going by 8s here, so each one is 1,000. So So that's 5,000, 10,000 is there. So this would be 8, come over here to 8,000, and this would be right here at about 7. And so that's what they're going to say, about 7 years. Okay, if you look back on page 158, your extra practice number 5, it's the same kind of problem. It's going to ask you the same thing. Tell whether it's exponential growth or decay from what we have here. So it's giving you a little situation about number of bacteria in a culture can be approximated by this model here, and here's our exponential model, and where T is the number of hours the culture is incubated. It wants us to tell whether that's a growth or decay. So just by looking at this, we want to look at what's inside the parenthesis here and see, is that more than 1 or less than 1. And so you can see this one is more than 1, so that will be growth. So it is growth, and the reason is because the B is 1.99 is more than 1. That's why it's growth. If it was less than 1, it would be decay. If it was 0.99, it would be decay. Then identify the hourly percent increase or decrease of the number of bacteria. Well, first of all, it has got to be, if it's growth, it's got to be an increase. So let's go ahead and underline or highlight increase, and maybe cross out decrease, because this is definitely an increase. We want to think about, okay, 1 plus what number would equal 1.99? That's a little easier to think of than the subtraction one. So you just know 1 plus 0.99 is 1.99. And that 0.99, that is our R, that is our rate. That is our rate of increase or decrease. In this case, it's an increase. And so we just look at that 0.99 part there, make that into a percentage by moving the decimal back 2 places. So that's 99%. It's a 99% increase on this one. And then for C, estimate the number of bacteria will be, or estimate when the number of bacteria will be 1,000. Go ahead and cross out these last 3 zeros. We're just going to look at 1,000. 1 million is a little bit big. So we're just going to look at 1,000 here, because we're going to go to the Desmos calculator and check this out. So I'm going to type in 100 and then the parentheses 1.99, and I'm going to put T up here. You can just say X though. I'm going to put X instead of T because X is on the calculator. So here it is. There's my 100, my parenthesis 1.99, and then my X is up here on top. And this is what the graph will look like initially. Well, we need to figure out when the Y is this number. So our Y is 1,000. So when, we're looking for when, that's the time when this number is 1,000. So we want to think, okay, well, what's our X going to be when Y is 1,000? So we need to go to where Y is 1,000 on the graph. So we got to go all the way up, and I'm going to just kind of zoom out here to kind of get a better bird's eye view of this and start to make my way up here. There's 800, 900, there's 1,000. Okay, so I can now click the graph and start to drag my point along. So I'm getting closer to 1,000, as you can see on the Y number there. 993, 995, 998, getting even closer. There's 999. So we're right there. And you can see, look at the X number at that point, 3.346. That's our answer that we want to use, 3.346. We can round that to 3.35. Just go to 2 decimal places. That's what I did here. So our answer there is approximately 3.35 hours. We're in hours. It's an hourly percent increase. And so time in this one, as you can see, is in hours. T is the number of hours on this one, so we want to label it with hours. Okay, so here's another one that we're going to put in on the middle of 157. So if you go to page 157, the middle where the notes is, right underneath the exponential decay function, we're going to put this one. So you can kind of just write down some of the main stuff here, like this equation right here. You don't have to write all the words or everything. The amount Y in grams of a radioactive isotope, chromium-51, remaining after T days is this exponential function here. Now this is a decay function, because it even tells you right here that it's decaying. A is the initial amount in grams. What percent of chromium-51 decays each day? We didn't have to figure out that it's decay. It told us that it's decay. So we want to figure out here what percent of this decays each day. So we're looking for R really in this problem. Is what we're trying to figure out, is the R. So A is the initial amount in grams. We really don't need to know that. So there's our first thing you can write. You can write this. We're looking to find out what R. You might want to even just say find R on this one. And so we got to start with kind of removing the t, bringing the t out of this fraction, and seeing this is really 1/28 and then the t, because if I was to multiply these 1/28 and t, I'd get back to here, t over 28. And so that's the first thing to see right there. And then we can just kind of keep working it through here. So now we can say the 0.5 to this 1/28th power. We can use a calculator for that. Let's go ahead and look at see how they would do that there. So we're going to put 0.5 as my base, and then I'm going to raise it up to, so the exponent button, and then 1 divided by 28, 1 divided by 28, and equals. And that's not what I wanted there, so it must be a parenthesis. I need to put a parenthesis in here. Sometimes that happens to where parentheses are important. So let's try one more time with putting 0.5 and then exponent, and I'm going to put a parenthesis now for my exponent, 1 divided by 28, and close the parenthesis, and now you'll see where we got that right now. So 0.03 actually equals, there it is, we got to put equals, sorry, because that was the actual 1 divided by 28 was that number. So there it is, 0.9755, and that's what they have here now. And so now they have this to the t power, so now that gives us our base. Our base number is this. We can definitely see its decay now from this number, because this number is less than 1. So now we want to figure out, okay, 1 minus what number will give us this number. We can do that on the calculator even. You know, we can kind of take away, we can say 1, minus this number. We can just put minus 1 on here. Minus 1 equals. And so that gives me a kind of a negative, but we're really going to just look at the 0.2 and so on. So you can see there it is, the 0.0245. That's what I had on my screen on my calculator, 0.024, and we raised that up to a 5. They rounded that one. That's our number that's going to go here for our rate. That's the one we're after. We're looking for R in this one, so we're trying to figure out this number. And it's asking us what the percent is here, right? What percent? So we got to change this decimal into a percent. Let's move it back 2 places. That's 2.45%. That's what we needed to know for this one. What was the rate, the R number in this? Okay, so you should have put that in the middle of page 157, at least this part right here, and the answer, what that should have been. Let's go ahead and take a quick little break and look at a joke of the day. Where does the one-legged waitress work? Well, everybody should know this one. IHOP. All right. Okay, moving on, staying on 157, really, where the concept here of compound interest is. Compound interest is an exponential problem. You can see here's the formula they're giving you for compound interest. It's an exponential formula with the nt power here. And let's look at what it says here. It says, consider an initial principal, P, deposited in an account. So when we're talking about compound interest, we're talking about money in bank accounts. So we love talking about bank accounts and money and seeing that grow. So that's what we like to see. This is a growth problem. You can see that the plus is right here because it's going to grow. We'll talk about how we can put some money into the bank and it will continue to grow if we leave it there and don't touch it. So P is the initial amount. P was like the A. So this is the same kind of model as we saw before, but just a little bit different of format. So A would be like your amount for the account, or how much money you're going to have in the account, or the balance of the account. Over here, P standing for the initial amount, the initial principal. That's the starting amount that you have in the bank. You got the 1 plus part. That's the same. And then you still have the R here, but now it's R over N. So R is the annual rate. It's expressed as a decimal. N is the compounded N times per year. So N is how many times this is being calculated a year. So compounded means kind of like calculated. So some bank accounts usually are calculated every month. Every month it calculates the interest and puts the interest in the account. Adds the interest to the account once a month. But other accounts might do it every 3 months, or might just do it twice a year. those kind of things. So you got to figure, okay, how many times a year? If it was every month, that's going to be 12 for n. If it was only twice a year, well, then it's 2 for n. And so that's why I have this here. I underline that part, and this is all the different ways we might see the compounding or the calculating of the interest. It might say annually, and if it says annually, that's just once a year. Semi-annually will be twice a year. Quarterly will be 4 times a year. Every quarter, it's like 4 quarters in a school year, 4 times a year. Monthly is the 12 times a year, and daily will be 365 times a year. So these are the possible numbers you could have really for the n, and the n is going to be down here. It's also going to be in your exponent as well. T stands for the time, and that's always going to be in years. And the amount A is in the account after that amount of time. Alright, so let's go ahead and try a couple of these on our extra practice now. Okay, so we're almost done. We just have these 2 problems left to do. We're going to use our compound interest formula. It says use the given information to find the amount A in the account earning compound interest after 5 years when the principal is $1,250. So the principal means that's the amount of money that you start with in the account. That's how much money you have in the account, and if you just left it there and didn't touch that money, how much money would you have in your account after 5 years according to these 2 rates here that they're going to show you compounded in these 2 ways. So it's just 2 examples of different ways we might see interest depending on the interest rates. So first of all, let's look at the interest formula. We got that compound interest formula again is this formula. A is our amount we're looking for. P is that principal. 1 plus r over n, and then it's to the t time or n times t power up here. You're multiplying the n and the t together. Okay, so to start with the information up here, these 2 things that's going to be 5 years and the principal is $1,250 is going to go for both number 6 and number 7. So our p on this one that we're going to plug in for both of these is the $1,250, and the t on this one for both of these is going to be 5. We're going to plug in 5 for t in both of these. So if you're like comparing 2 bank accounts or 2 different banks, this one has a interest rate of 2.25, this one's got an interest in 1.25, then most likely the 2.25 would be the one you'd rather go with. This should be having more money at the end of those 5 years than this one would have. This one's compounded quarterly, this one's compounded daily, but we'll see how that kind of works out. But just by looking at it right off the bat, this one looks better just because the interest rate is higher than this one down here. So to start off with the number 6, our rate, we got to change that into a decimal, so we're going to move the decimal to the left 2 places, so 0.0225, and then our compounded quarterly, just like we saw that I had you write down before, make sure you write those down underneath that compound interest formula, that this one's 4 times a year, quarterly is 4 times, so n is 4 on this one. So now we just start to plug in everything. So A equals, and our P is that $1,250. So $1,250 for the P. Then we're going to have our parenthesis with 1 plus the fraction. So 1 plus a fraction, and on top we have the R, so this number is going to go on top, the 0.0225. That's up on top. N is on the bottom, so 4 goes on the bottom of this. And then over here we have n times t, so n is 4 again, but t is 5, so we're going to say 4 times 5 out there. So that's not hard to do. We should be able to plug everything in that we need here. You just now need to calculate this. So we will be using the calculator to help us calculate this. We know we can do 4 times 5, that's 20 for the exponent out there. Let's do that first. Let's just make that 20. But then we have inside here, we're going to make all of this into one big decimal. You might think, well, how do we go from this to this? Well, I'll use my calculator. Let me show you. Let's clear this off. Bring this down here. So what we're going to do is we're going to first figure out what this is and then just add 1 to it. So I'm just going to do my 0.0225 divided by 4, and that will equal this number. And I'm just going to add 1 to that, so just put plus 1, and that gives me the number right there that you see inside my parenthesis, 1.005625. It's exactly what we have in the calculator right here. So now that this is on my screen, what I can do next is just raise it to the 20th power. That's what I'd want to do next to figure out this next step. and then multiply it by 1250 after that. So we're going to raise this up. I'm going to hit the X to the Y button to give me my caret. And I'll put 20. I don't need to put the parentheses because that's not a fraction. We're just going to put the number 20 there. And that equals this number now, 1.1187. So that will be something like this here. So our 1250 is being multiplied now by 1.1187. I just rounded it a little bit. But if you keep your number here on the screen, then you don't need to worry about rounding. You just can keep it there. We're going to multiply this now times 1250. So times button, 1250, and equals. And that gives us our answer for this one, 1,398. And we want 2 decimal places. We're talking about money. This is going to go up to 40 cents. So that's what we're going to see here. There it is. So $13.98 and 40 cents. That's how much we would have at the end of 5 years if we left this $12.50 alone in the account that earns 2.25 interest that's compounded quarterly. So not too bad. I mean, that's a good extra $100 or so, almost $150 even there, for doing nothing and just sitting there in the account. Let's check out this one and see how much money, and then we can kind of maybe compare these two. But let's do the same thing on this next one. Our rate here, we're going to move the decimal back in front 2 places, 0.0125. The compounded daily, remember daily just means 365 days a year, so 365 is the N on this one. So don't forget, you should have copied those down there so you know what to put. And then if we start just to plug things in, so A equals, our principal again is at 1250. And then we're going to have our 1 plus the fraction in that parenthesis, so we'll put that down. And then we're looking for R on the top of the fraction. That's going to be our 0.0125 number. And then 365 is going to go below that for the N. And then for the exponent, it's N and T, so 365 times 5 will be out there. So 365 times the 5 goes as your exponent. So we're going to do the same thing and figure out what this is first. We can multiply 365 times 5 also. So using our calculator, I'll clear this one off now, and we're going to start with the top number here, divide it by 365, so 0.0125 divided by 365. That equals that number. And then we just want to say 1 plus that. So plus 1 equals, and there it is. So 1 point, a whole bunch of zeros. So as you can see, that's what we'll see over here. So there it is, 1.1234 zeros, and then I rounded it to 34. If you multiply 365 times 5, that's 1825. You can do that and see that on your calculator. And now we want to raise this now, it's on the calculator screen, to 1825. So I'm going to hit my exponent button here. The X to the Y on this calculator is what it says. And I'm going to raise it to the 1825. And now we'll get this number, 1.064 and so on. So that will look like this. So 1.0645, I just rounded that. And multiply this now times 1250. Where we go here? There we are. So now just times the 1250 and equals. And we see it says 1330, 2 decimal places here will be 62 cents. So that will give us our answer here, 1,330, 62 cents. So as we compare these two, then yes, this definitely was a better one that we got more money from. 1398 was definitely better than 1330. So what we thought right away, that the interest rate, a higher interest rate, will definitely give us a better return in the end. It'll give us more money in our bank account if we're going to earn higher interest. That's a whole 1% higher than this one. Even if it's compounded daily instead of quarterly, it still is much better. Usually the more compoundings typically is better. So if these were the same rates, compounded daily would have been probably a little bit better than quarterly, but because this interest rate was so much bigger, that's why it was definitely better. Alright, so that concludes 6.1. So you should be ready to go on to the assignment for 6.1. And if you have questions, just make sure you find me and ask me those questions that you need to ask. Alright, I'll see you guys in class.